Thank you, Sam. Okay, so thanks everyone for coming to this, our second Canvas talk of the year. I'm Tyrone Woods. I'm a Plaska Fellow at HAA, and I'm coming to you from the traditional and ancestral territories of the Coast Salish peoples. Our speaker today is Dr. Anna Ordog. She is a postdoc jointly through UBC Okanagan and DRAO. And before that, she did her PhD at the University of Calgary, if I'm not mistaken, with Joe Bra. And so today, I have the wrong thing open. She's going to be telling us about polarized radio observations for exploring the three-dimensional galactic magnetic field. So why don't you take it away, Anna?
Sounds good. Thank you so much for the kind introduction, Tyrone, and thank you for the invitation and the opportunity to give this talk. So if at any point you can't hear me well, I've been having a bit of issues with my mic, just let me know and I can try to adjust those settings. So before I begin, I would also like to acknowledge that DRAO, where I currently work, is located on the traditional, ancestral, and unceded territory of the Syilx Okanagan people, and I'm very grateful to have the opportunity to call this place home right now. So this talk today is going to be a little bit of a rambling tour through my adventures in radio polarization in the last several years. And I do also want to acknowledge my collaborators and mentors and the students who I've been working with over the past few years, and whose work you will see scattered throughout the slides here. All right, so this is the kind of outline for the talk today. So I'll start with a quick introduction into why we're interested in studying the galactic magnetic field. And then I'll talk about the main tool that we use for this purpose, which is Faraday rotation. And then I'll dive into some of the work that I did in my PhD with the Canadian Galactic Plane Survey dataset, as well as the Global Magnetoionic Medium Survey. And then the last few minutes, I'll spend talking about the work that I'm currently doing at DRAO with some data from the CHIME telescope, as well as a new single dish radio telescope that we're commissioning for a survey that we have planned. All right, so it has been known for several decades now that the Milky Way galaxy, as well as many other external galaxies that we observe, hosts a large-scale magnetic field, and this has been determined to play an important role, for example, in providing pressure balance against vertical gravitational collapse of the galactic structure, and it plays a role in processes like star formation and cosmic ray acceleration. What we know to date about the Milky Way's magnetic field is that on the largest scale, as viewed from the North Galactic Pole, the magnetic field lines are oriented primarily clockwise, with one apparent large-scale reversal that I'll talk about a little bit later. And so we have these large-scale structures that are coherent over the scales of the spiral arms, and they more or less follow along that same type of pattern. And then there's turbulence on smaller scales and smaller scale magnetic field structures that tie into the larger scale structure in molecular clouds and star forming regions and such. Overall, the average strength of the magnetic field is around on the order of a few microgauss, and the origin of the field is thought to be a galactic scale dynamo. And there's a lot of work currently being done to do simulations and models to work out exactly how that process took place and how the field formed and is evolving. And so we need observations to try to constrain those types of models as well. And there's a lot still that remains unknown. And so the goal with my work has been to try to contribute to our understanding of the three-dimensional structures in the Milky Way magnetic field with some observational techniques that are kind of evolving as the years go by. So that's the quick introduction. And then, as I said, the main tool that we use is Faraday rotation. So this is this phenomenon whereby if you have a linearly polarized radiation that passes through a magnetized electron gas, such as the interstellar medium, its plane of polarization will undergo a rotation, and the amount of that rotation, if my slides will show it, whoops, is given by this equation here. And so it depends on the wavelength squared of the polarized emission, as well as the integral of the electron density multiplied by the line of sight component of the magnetic field. And that's integrated along the line of sight from the source to the observer. And the quantity that's in that integral is known as the rotation measure. And in the simplest cases, there's a linear relationship between the wavelength squared and the polarization angle. And so you can observe polarized emission over a range of wavelengths and work out a rotation measure just from a linear fit. So the simplest case that has really quite often by this point been used as a probe of the interstellar magnetic field is extragalactic point sources. So these are sources for which we can assume that the emission occurs basically at a single point in space, and then the rotation occurs just through the galactic volume that we're interested in. And so for these kinds of cases, we can do this linear analysis to determine a rotation measure. And one of the pieces of information that we can get from this is that if we have a positive rotation measure, this indicates an average line of sight component of the magnetic field directed toward the observer. And then the opposite is true if the magnetic field is directed away from the observer. Now, in addition to these point sources that have been used as these probes, there is also polarized emission through synchrotron emission coming from basically everywhere within the galactic volume as well. And for this type of emission, the emission and the rotation are mixed within the same volume. So the situation can get a little bit more complicated because you can have a large amount of emission, a large amount of Faraday rotation happening to emission that's coming from the far side of this volume. At intermediate distances, you would get slightly less, and from nearby distances, you would get little or no rotation at all. And all of this emission combines in some complicated way at the observer, where we are trying to make these observations and trying to determine what the rotation measure is. And so the question is, what is the rotation measure when all of that emission is combined? There is a simple case referred to as the burn slab scenario, where the electron density, magnetic field, and the polarized emission in the volume that you're looking at are all uniform. And in this case, it turns out that if you just calculate a rotation measure as a linear fit to polarization angle versus wavelength squared, you get a result that is half of the value of an equivalent point source that would be located on the far side of that slab. And so with that, I'll show the sort of first set of results that was one of the projects in my PhD. And so this was studying both extended emission and compact point source extragalactic rotation measures from the Canadian Galactic Plane Survey. So the CGPS was this large scale survey that was done in the late 90s and early 2000s. To map out the galactic disk as seen from the Northern Hemisphere from the DRAO. And it was primarily done with the synthesis telescope at DRAO. And so this is this interferometer array. And one of the data products from this was maps of continuum polarized emission in 4 closely spaced frequency channels centered around 1420 megahertz. And so that's what you see in the map at the top here. The background is that polarized emission. And from this, a set of point sources were derived from the set of observations. And this was published as a rotation measure catalog by Van Eck et al. In 2021. So the dots that you see on this map are just those point source rotation measures, and they're color coded by their rotation measure value, which is given by this color scale in rads per meter squared. There's a question in the chat about fitting the rotation angle versus wavelength squared, and there's an n pi radian ambiguity. So this ambiguity, yes, this is a very real thing that has to be dealt with. For the particular case of the CGPS, having the frequency channels very closely spaced actually helps resolve that ambiguity, because we know that from one channel to the next, we're not having more than a pi rotation. But we can talk about that more at the end if there are further questions on it. So with this, apart from just this rotation measure catalog, we also have, like I said, this diffuse extended polarized emission in the background. And so one of the projects that that we set out to do was to basically just determine rotation measures for every pixel in that in that background from that extended emission in the same way, just by doing these linear fits of polarization angle versus wavelength squared, the same way as was done for the point sources. And the way that we analyzed the results from this was to look at the variation with galactic longitude. So in this plot here, we have binned both the extragalactic point source and the extended emission rotation values in longitude bins across the entire CGPS range. And this is the result. So the purple pink line shows the point source rotation measures, and the green line is the extended emission rotation measures. And you see that they actually track a very similar trend with longitude in the galaxy. And furthermore, if we go ahead and multiply the extended emission rotation measures by 2, you see that the lines actually match up really well for the most part. There are a few exceptions. This low longitude region, that's where the magnetic field reversal is. We'll talk about that more a little bit later on. But it was interesting to see that basically we are getting for vast regions an approximate ratio of 1/2 between these extended emission and extragalactic point source rotation measures. And so this was kind of an interesting result, partly because we wouldn't really expect the volume of the interstellar medium to actually be a burn slab scenario, that simple scenario where all of the parameters are uniform. So one of the other things that we did in this paper was to do some very simple sort of toy models to try to work out what other kinds of scenarios might be leading to this result. And so what we did was, instead of having the electron density, magnetic field, and synchrotron emission be uniform within the galactic volume, we modeled these with just some very simple exponential models where each of the parameters has some characteristic scale length, and these values drop off with galactic radius. So these are the 3 parameters, but they can basically be collapsed down into the exponent in this equation here, which has this ratio of a scale length associated with phi, which is the Faraday rotation in this case, and S, which stands for the synchrotron emissivity. And what this equation is just a polarization profile as a function of the different values of Faraday rotation that you would get from different depths along the line of sight. I won't go into the details of the math here, but the point with this is that we could kind of break this scenario down into 3 different regimes. One where the scale lengths of the Faraday rotation and the synchrotron emissivity were the same, so that ratio is equal to 1, and then the cases where that ratio is either greater than or less than 1. And so you get this polarized intensity profile as a function of the amount of Faraday rotation, essentially, for the 3 cases. And so we can take that and kind of observe it as we would with at different wavelengths, and determine what polarization angles would result from that. And then we get a set of scenarios like this with the polarization angle as a function of wavelength squared. And then taking the slopes at any point along these plots would give you the corresponding rotation measures. And so we did that, and we took those rotation measure values and divided them by the equivalent point source rotation measure values that you would get. And that's summarized in this last plot here. So essentially, this is this ratio of extended emission to extragalactic rotation measure that I was talking about as a function of wavelength squared. And so the interesting result from this model was that we can, in fact, depending on the observing wavelength range, actually get a ratio close to 0.5 for these models that are not just the burn slab scenario. They're still very simple models, but they're a little bit more realistic in terms of explaining what actually might be going on in the galaxy in terms of the ISM parameters. So the takeaway from this was that the extended emission and the extragalactic point source rotation measures trace similar trends as we saw in the CGPS data. And we can construct very simple models that deviate from a burn slab scenario that can account for this ratio. That was the first part. And then the second part of that, I mentioned the large scale magnetic field reversal. So this is something that we studied a little bit in our 2017 paper. The plot on the top left here is showing the top-down view of the galaxy, and the arrows indicate the approximate directions of the magnetic field. So we have this predominantly clockwise orientation, and this is where the reversal is thought to exist in the galaxy. So the results from this study showed that in the region of the reversal, there's actually this, in relation to the galactic disk, there's sort of this diagonal orientation of the boundary that separates the opposing magnetic field directions. So the top panel here is showing the CGPS rotation measures. The filled in circles represent positive, the open circles represent negative. And so you see this type of gradient here. And we see the same structure in the extended emission rotation measures. Here I'm showing these color-coded, blue for positive and red for negative on this side of the boundary. So one of the questions that we asked after this result was, does this pattern continue outside of the galactic disk at higher and lower galactic latitudes? And so for that purpose, we got some new observations with the synthesis telescope at DRAO. To fill in these two regions. Basically, we were aiming for these regions that are kind of close to that boundary we were seeing, and these are the results from that. So this map here again is just showing the extended emission rotation measures. The difference between this and the one I showed on the previous slide is here I'm not doing any kind of filtering of any of the data for signal to noise or anything like that. This is just all of the pixels in the map. But you can see the structures here. So this is this positive region, and we see that with the new data set at the low longitudes, we would have expected negative rotation measures if this pattern follows that diagonal structure. And indeed, we do see that. But at the higher latitudes, that pattern kind of breaks down and becomes less apparent. So that was kind of the interesting result from that. And within this data set as well, so within this mess of pixels, we can also pick out point sources and do extragalactic point source rotation measures the same way as was done from the CGPS catalog. And so in this version of the plot, each dot, the inner circles represent the rotation measures of the point sources, and then the circles surrounding them represent the extended emission rotation measure in around that same region around those sources. And so with this, again, in this lower latitude region, we see really good agreement between the extragalactic point source and extended emission rotation measures. They're the same color and on this scale. But at the high latitudes, generally the magnitudes of the rotation measures are lower, and there's just generally more confusion and less of a clear correspondence between those. So we can look, now that we have, with these new portions of the data set, we have more extent in latitude. So instead of just looking at things as a function of longitude, we can look at the latitudinal variations as well. And so in these plots, I'm just going to step through various longitude ranges, and now I'm plotting the rotation measure as a function of latitude for the extragalactic point source in blue and the extended emission in red. So if we just step through those, the general trend, again, we see is that the rotation measures increase with latitude for both types of sources, and then the trend sort of tapers off towards the higher longitudes. And this result was corroborated by another study. This is a very large array study of another set of compact extragalactic point sources by Ma et al. In 2020. And so this study covered a region, this is adjacent to the CGPS data region, so just a lower longitude portion. And they found this similar result, where from longitudes from about 40 up to 52, they also do see this increasing trend in the rotation measures as a function of latitude. So takeaway from that part of the study was that the large-scale magnetic field reversal in the Milky Way has this latitudinal structure as well over quite a large range of galactic longitudes. And so this is important to try to fit into models that are being created of the large-scale galactic magnetic field that take into account reversals. These reversals aren't happening only, along one axis. There's complicated geometries that need to be taken into account. So those are the results from the CGPS. So moving right along to the next part here is the global magnetoionic medium survey. And so for this, I have to actually take a little step back and talk about Faraday rotation a little bit more, because I had mentioned the scenario of mixed polarized emission and Faraday rotation and the burn slab scenario. And it turns out that not all cases are that simple, and we don't always have just a single value of rotation measure that's going to adequately describe the line of sight that we're observing. And so we have to look at something called Faraday complexity. And here, the equation that I have written, this is basically the same as the rotation measure equation, but now I've replaced rotation measure with this quantity phi, which is called the Faraday depth, and it's a function of z, the physical depth along the line of sight, because we need to account for Faraday rotation coming from these different depths. And again, if we just take a step back to this point source case where we have emission at a single point, rotation through the volume, in this case, the rotation measure is just the Faraday depth value corresponding to the location of that source. And so if you were to plot something like this, which is a Faraday depth spectrum, that's what we're building toward here, the polarization as a function of Faraday depth, you would just get a single peak at the value of the rotation measure. And again, for these cases, it's adequate to just have a handful of polarization angle measurements at different wavelengths, and you get the linear fit rotation measure. For the extended emission, if we want to consider these more complex cases, again, just cartoon depiction of mixed emission and rotation within some volume, really what you're getting is this type of Faraday depth spectrum where you have polarized emission over a whole range of different Faraday depths. And so we're basically trying to work out what the shape of that structure is. And again, a single rotation measure does not always adequately describe that profile. We need to consider the spectrum, and for this we need broadband observation, so much more than the four narrow channels that we had with the CGPS data. So essentially what's happening here is there's a mapping between the Faraday depths as a function of physical depth and this Faraday depth spectrum. And the way that we can work out what the Faraday depth spectrum is, again, I won't get into the math, but it turns out that there's a Fourier transform relationship between the polarization angle as a function of wavelength squared as we observe it, and this Faraday depth spectrum. And the process of recovering that spectrum is called rotation measure synthesis. All right, so once again, just the simple point source case, if we were to do these measurements over a broad range of wavelengths, this is what we would expect to see, just a single peak, a single spike at the rotation measure of that source. With an extended structure, what you would expect to see is this, the entire extended structure in Faraday depth. But what actually ends up happening because of limited sampling in wavelength space is that a structure like this actually breaks up into two peaks at the sort of the far edges of that structure. And so to understand what's happening with that, we need to consider some parameters that have to do with Faraday rotation. One of these is the maximum Faraday depth that you can detect depending on the sampling that you have in your frequency or your wavelength space. And it turns out that this one's fairly easy to get fairly high rotation measure values, higher than what we would expect to actually see in the Milky Way, as long as we have frequency channel spacings on the order of a few megahertz. And so this part's easy to take care of. The next two are a little bit more interesting. The Faraday depth resolution This is proportional to, inversely proportional to the range of wavelength squared values that you have in your survey. And so this is going to, having a narrower resolution is going to allow us to basically observe multiple narrow Faraday depth features along the line of sight. And then the last component is the broadest detectable Faraday depth scale. And this is proportional to 1 over the shortest wavelength in your survey. And this is what's going to determine whether a structure like this is going to break down into, into two individual narrow structures. So ideally what we want to have is this broadest structure being larger than the resolution. That's how we want to ideally choose our survey parameters. And so that brings us to the GMEMS survey and the corresponding Faraday depth maps. So GMEMS is this global project with scientists from all around the world, both northern and southern hemispheres, basically trying to map out the entire sky in Faraday depth space. So the component that I've been working with is the DRAO 26-meter GALT telescope component, covering this frequency range. And so this was completed a few years ago and published last year. So the plot here is showing the frequency coverage versus the wavelength squared coverage. I'll come back to this plot later on when I introduce another data set that we're working with. But again, just focusing on these two parameters, the resolution and the broadest structure detectable. The plot here is illustrating the resulting parameters for the GMEMS survey, so that the space between these dashed lines, that extent is the broadest structure that we can detect with it. And this Gaussian shaped structure, this is known as the rotation measure spread function. And essentially all you have to know here is that the full width half max of that is what's telling you your Faraday depth resolution. So with GMEMS, we don't quite achieve this criterion of having really narrow resolution and wide sensitivity to wide structures, but there's still a lot of useful information that we can get from this data set. So I'm showing here a couple of examples of spectra from the GMEM survey. So these are just along 2 different lines of sight. Never mind the dashed lines and the solid black lines here, focus just on the solid blue lines. These are showing the actual Faraday depth spectra. So the top panel is showing a case where we have a relatively simple line of sight with a single Faraday depth component. And then the bottom panel is showing a line of sight where we have two components appearing. So there's some Faraday complexity that we can see there. Another thing we can do, another way the way to produce maps out of something like this is we can collapse each of those spectra down to a single value by calculating a first moment. So that's just a weighted average of the polarization intensity weighted average of the Faraday depths along that line of sight. So if we get a value like that for each point along the line of sight, that is more or less we can call that the rotation measure as derived from RM synthesis. And then we can make a map of that. So this is the resulting map from the GMEMS high band north sky. And again, this is just the color coding is just showing you the rotation measure values. And so you see lots of interesting structure in here. You see evidence of reversals and differences between the northern and southern hemispheres. And there's a whole host of work that still needs to be done with this survey to kind of analyze and compare with other surveys as well and see what we can work out from this. Here's an example of Faraday complexity that we see in this survey. So this is the region shown here is the H2 region, Sharpless 227. And the interesting thing that we found with this was that within the H2 region, we're getting these double peaked structures in the Faraday depths, whereas outside of it, it's the kind of more common a single peak feature. And we compared these to extragalactic point source rotation measures from the Taylor et al. NVSS catalog. Those are the dots shown on the left panel here. And their values are shown by the vertical green lines in each of these two spectra. So we get this result that for the single peak spectra, those peaks agree well with the point source rotation measures. And then in this double peak scenario, it's agreeing with one of the peaks in the spectrum. So we looked at just some simple models that could account for a structure like this. And so because this is an H2 region, there's enhanced electron density in that small region of a small portion of the line of sight that object occupies. And so that, along with even just a constant magnetic field, can lead to this type of structure where we have this double peaked Faraday depth spectrum. So again, just a very small example of the types of things that we can do with this data set. And I don't have time to go into further details, but there are this data set, GMIMS High Band North, is really proving to be very useful in probing the magnetized interstellar medium, and there are several projects underway making use of this data set. So stay tuned for more from GMIMS. And then finally, from the portion of my work that I was doing during my PhD, I was actually also doing some comparison and combining of the CGPS and the GMIMS data sets. So just really quickly, comparing the types of observations that we have, the CGPS again is with an interferometer telescope. So this is sensitive to small spatial scales, so it has high spatial resolution. Whereas a single dish telescope, like the one that was used for the GMM survey, is sensitive to extended structures, but doesn't have that kind of spatial resolution. And so ideally what you want to do is combine these types of data sets to get the full spatial structure of whatever it is that you're mapping. And so I basically went ahead and attempted to do this with the CGPS and the GMIMS data sets in the context of making Faraday rotation maps. So recall that the CGPS only had these 4 frequency channels. So basically what I had to do was create 4 equivalent channels from the GMIMS data set that I could basically add together channel by channel. And so looking at the GMIMS version of this map, you can already see that there are actually substantial differences between what the rotation measures end up looking like from these 2 data sets. And in part, this is due to the differences in beam sizes of the 2 telescopes leading to something called beam depolarization, which effectively limits the distance along the line of sight that you can see with this type of data set, with the single dish data set. So there are differences between those, but in any case, I went ahead and combined these. Those are just the same 2 images that I showed on the previous slide. And then on the right is the resulting combined rotation measure map. And so it's kind of interesting to see that a lot of the small scale structures that you see in the CGPS remain, but this large dominant negative component, for example, from GMIMS is starting to appear here as well in the combined data set. So this part is still a bit of a work in progress. This is as far as I got to with this in my PhD study. So I intend to continue working on this to see what kind of information we can gain from having a combined data set like this. And going forward, something like this is going to be very useful because the synthesis telescope at DRAO is undergoing an upgrade in the next several years to allow it to have broadband capabilities similar to and beyond the GMIMS data set. So we'll be able to properly combine data from those 2 data sets or from those 2 telescopes over a much larger range of frequency channels. So again, there's more to be done on that in the future. Takeaway point from this is that these combined data sets do contain information across a broad range of spatial scales, but because we are probing different depths in terms of Faraday rotation, this kind of complicates the picture a little bit. All right, so that was the that was the portion of the talk about my PhD studies, and so I think I'll spend the last little bit here talking about what we're currently working on at DRAO with the CHIME telescope, as well as this new 15-meter single dish telescope. So just putting these in the context of GMIMS, the GMIMS data that I showed were just one component of the 6-component survey that is planned and underway. Some parts of it are published already. So this was the northern component with the DRAO 26-meter that was already published. There's a component at low frequencies from the southern hemisphere with the Parkes telescope in Australia that has also been published, and then other components that are in various stages of planning or data collection or data processing. And so the CHIME data that I'm going to show and this DVA2 single dish data are going to provide the low frequency component in the northern hemisphere, essentially. All right, so the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, which most of you are probably familiar with to some extent, is this transit telescope consisting of these 4 cylindrical reflectors that was built a number of years ago at DRAO. And its primary purpose is to study the cosmic microwave background. But it also produces really high quality maps of the galactic foreground. And so the galactic science team, of which I'm a member within CHIME, has been using these to study the galactic foreground as well. Now, CHIME itself is also an interferometer, so although it can detect fairly broad structures and has fairly short effective baselines, it is technically missing the shortest baselines. And so this other telescope, this 15-meter dish called the DVA2, can provide those short baselines, and it's going to have similar frequency coverage to CHIME. So it'll be nice to be able to combine those data sets once they're both available. Yeah, and it will be able to be used as a calibration tool, both in terms of polarized intensity and polarization angles from the CHIME data. So returning to these Faraday depth parameters with CHIME, if you compare this to the purple region that was for the GMIMS high band north, CHIME covers a much broader extent in wavelength squared. And so this results in a much narrower RMSF rotation measure spread function. That's shown by the green curve in this plot compared to the purple for GMIMS. And so ideally, if you were able to combine those 2 data sets, then you would get the advantage from GMIMS high band north of having the sensitivity to broad structures and the Faraday depth resolution that you would get from the CHIME data. So that's sort of the ultimate goal, and why we want to combine data sets from a broad range of different frequency coverages. So one of the advantages with CHIME is that it can actually map the entire northern sky as seen from our latitude once per sidereal day. The sky just drifts overhead, and we can create a map. If you stack those maps over several weeks or months or years of observing, then you can improve your sensitivity, and obviously that's needed for the cosmology side of working with CHIME. But what we found was that for the initial studies that we did with the galactic foreground polarization maps, it was actually sufficient just to take 1 day's worth of data. And what I'm showing here are Stokes Q and U maps. I didn't get into details of what Stokes Q and U are. They're basically just the components of complex polarized emission. And so we created these maps. These are at a single frequency, and compared them to these previously available data set, the Dwingelo data set, which was available just at a handful of frequencies and within the CHIME band. And we see that we're getting really, really similar looking maps. And so that was encouraging to show that we're on the right track for calibrating the CHIME polarization maps and making use of them in rotation measure synthesis and Faraday tomography. So this is very much a work in progress. This is a kind of a brand new result here that I'm showing. So on the left is the GMIMS high band north first moment map of Faraday depths that I showed earlier. And here it's just masked to the same region that we have available in CHIME and galactic coordinates. And then on the right is the CHIME version of that map. So again, just from that single day of observations from CHIME. And so we were really struck by the degree of correlation between these two maps, just looking at them by eye, and how much of the same large scale structures are being probed in terms of the Faraday depths. So again, this is very much a work in progress and lots to do here still, but these maps are looking really promising for feeding into this larger GMIMS project. And I do just want to say that the small team of which I'm a part, who are studying these galactic foregrounds in CHIME, is just a tiny fraction of the entire CHIME team who has worked, extremely hard over the past several years to build this instrument, to figure out how to get data off of it, process those data, keep the instrument running. It's a telescope with no moving parts, but everything else about it is very dynamic. So it takes a huge team of people to produce, to get to the point where we can produce these beautiful maps of the Faraday sky. So that's just a shout out to the entire CHIME team for getting us to this point where we can do this. All right, so that was the CHIME component. And then lastly, I'll talk a little bit about this DVA2 telescope. Again, so this is the telescope itself. It's located at DRAO. And again, we have this large team of scientists, engineers, technologists, everyone who's worked really hard to make this instrument operational and get it to the point where we're actually commissioning it for the purposes of science. So I should just say that the name of this telescope, DVA, it stands for dish verification antenna, which is perhaps not a very informative name, but it comes from the fact that this telescope was initially built basically as an engineering prototype for the SK. So it was an engineering project initially, and then we've kind of taken over to turn it into a science project. So this is the core science team led by Tom Landecker and myself, and we also have a number of students who are contributing. Luca Galler, who's a University of Waterloo co-op student, is working with us currently. Rebecca Booth from UFC is a PhD student who will continue to work with us on this project over the next few years. And Ian Kennedy was a UBCO summer student last summer who helped us with the initial steps of the commissioning. So again, just a shout out to the folks involved in making this project happen. So this is the telescope itself. The dish is this 15-meter wide offset Gregorian reflector. It was built as a precursor prototype for the SKA. It has the surface precision can be used up to something like 50 gigahertz, which is completely overkill for what we need for our purposes at low frequencies. But nevertheless, we have this great instrument to work with, so we're implementing it for the use of this low frequency polarization project. And the receiver that we have up on the telescope right now, it's referred to as the Band 1 receiver. It was built at Chalmers University in Sweden. It's an ambient temperature receiver. There's no cryogenics involved or anything like that. And it operates between 350 and 1050 megahertz. And this was the exciting moment last May when the receiver was finally installed up on the platform of the telescope. And so we were, since then, we've been able to connect everything up and start testing and commissioning. So here's an example of a spectrum that we get from our receiver in this frequency range. So this is just showing the total power, just observing a random point on the sky in the two polarization channels, which are right and left hand circularly polarized for the case of this telescope. And one of the things, of course, that stands out right away is the amount of radio frequency interference that we have to deal with. So Luca Galler, our co-op student, has been working on some RFI excision methods. Trey Wenger, who's on the call as well, has helped us out with this stuff a little bit as well. It's a work in progress, but this is an example showing the differences between daytime and nighttime observations. So these are just histograms that Luca has produced of observations from various times, and the blue lines are basically the counts of the channels that we have to get rid of because of RFI. And so you can see that in these low frequency bands, there's a little bit more during the daytime than the nighttime. So that's one reason to observe only at night rather than during the day. But nonetheless, there's a lot of channels that we have to get rid of. So unfortunately, it's a race against the cell phone industry to be able to gain some data out of this and kind of pick it out from amongst the RFI. The other thing that Luca has been working on is doing raster scans of bright radio sources on the sky. And the purpose of this is twofold. One is to determine the pointing accuracy of the telescope. So the plot here shows just a raw raster scan of one of these sources, and then on the right is an interpolated version where you can see the shape of the beam. So a point source, for observing a point source, single dish telescope like this is just going to take on the shape of the beam basically. And so you can see we do have a small offset. This is where we expected the source to be. That's not quite the center of where it ended up in the scan. So there's a bit of an offset. We have to try and implement a pointing model in the telescope to correct for that. And then the other thing that Luca has been doing with this is analyzing the shape of the beam. So again, this plot is just the raw data from this raster scan, and then she has done a Gaussian fit to that, from which, repeating that across all the frequency channels that we have, we can build up a picture of basically the beam width as a function of frequency. So it's more or less what we expect it to be. The slight deviations here, maybe we have to try to account for, but we're well on track with this part of it. The scanning technique we're going to be using, because this is an alt-az telescope that can scan in azimuth very quickly, we're adapting a technique developed by Coretti et al. For the S-Pass survey done with the Parkes telescope, where we just scan back and forth in azimuth at a constant elevation. And if you translate that into coordinates in RA and DEC, you get these kind of two sets of scans that are kind of in orthogonal direction. So you've got eastward scans and westward scans, and then if you overlay them, they produce this crisscross pattern from which you can do a basket weaving and a map making process to piece together a picture of the entire sky. So this is the survey itself is expected to take several weeks worth of nighttime observing to collect all of this type of data. And we have this map making software, like I said, that we're adapting from the S-Pass survey paper. And one of the contributions from summer student Ian Kennedy was to produce some mock scans from the GMIMS data that we can just use to test that map making software. So that's well underway. And then this is just to show what the scan pattern looks like in galactic coordinates. Again, that crisscross pattern from the east and westward scans. That's just scanning at a single elevation. If we want to go to lower declinations, we have to scan at a lower elevation, and then you build up a map of the sky that looks something like this. And so we did a first set of these azimuth scans just as kind of a proof of concept just before the winter break. So we did 7 hours worth of observing. This was just during the daytime. So the plot here is just the raw data. These triangles are the back and forth scans in azimuth, and then the orange and blue are the data. So in RA and DEC, if you piece that together, it looks something like this, and in galactic coordinates, something like that. And of course, this is extremely sparsely sampled. This is nowhere near what we can actually use for science. But again, it was just to illustrate that the telescope works. We can collect the data. The scan pattern works. And already, even with just these few scans, you can start to recognize some of the familiar features that you would expect to see in the galaxy. So the galactic disk is showing up here. You've got bright sources like SIG X and SIG A. And so yeah, that was just kind of fun to see, collecting just a few hours worth of data, and we already have something of a map of the sky. So I'll end there, just to allow time for questions. But basically, yeah, we're kind of moving from working with only a few frequency channels and determining rotation measures for point sources or diffuse emission and the information we can get from that, to these really broadband surveys where we can start to probe the Faraday complexities along the line of sight and really work towards building up a three-dimensional model of the Milky Way's magnetic field. So I'll end there. Thanks for your attention, and sorry for the kind of crazy rambling talk.
No, thank you very much. Substantive round of virtual applause. That was really, really great. It's humbling to see how much is going on at DRAO. It's really great.
Thanks for that.
We've got a bunch of questions. I see William Wall already has his hand up. He also has a couple of questions that have been in the chat for a little while.
I think I answered one of them.
Answered the first one, and then they kept coming. William, why don't you start and take it away? You have to unmute, William.
Oh, you're offering me a chance to read what I wrote.
Oh yeah, I wasn't sure if you had more questions too. Yeah.
Oh, I have lots of questions, but I don't want to.
I suspected so.
Well, I can go ahead and address the one about so you're asking about large scale reversals and whether they have anything to do with the spiral arms. And so yeah, there is some evidence of there being kind of the boundaries between spiral arms being associated with this reversal. But it's not, this isn't 100% clear, and there might actually be, it may not be exactly aligned. There may actually be some sort of intersection of the magnetic field lines with the spiral arm. So it isn't an exact alignment, but certainly that's an interesting area of research to try to figure out what the causes of that reversal are. So.
Right. Yeah. Well, actually, what I was going to ask you also is, have you compared your results with other data sets? For example, you said you can get the electron density in the interstellar medium on large scales. How does that compare with, say, pulsar dispersion measures? Mm-hmm. Or also, what about Zeeman observations of polarization? Have you compared with those?
Yeah, so I've done a little bit of work with pulsar rotation measures. Mm-hmm. The difficulty with those is, well, sort of twofold. One is having accurate distance measurements. So you need to know what pulsars are useful if you know exactly where they're located within the galaxy, because then you know what distance.
Yeah, I meant pulsar dispersion measures, right?
Pulsar dispersion, yes, yeah. So pulsar dispersion measures can be used to construct electron density models as well. And so yeah, there are a few models out there that are derived from those sorts of data. I myself haven't done too much with that, so I'm probably maybe not the right person to ask about that, but certainly that is one of the pieces of information that needs to be folded in to actually derive magnetic field strengths and not just directions from rotation measures. Yeah.
And Zeeman observations?
Zeeman observations, my understanding is that they're not as well suited to sort of large scale global studies. So this is not something that I've that I have much experience in, but certainly, yeah, they are another avenue of investigation for.
Right. Well, overall, this seems very exciting to me, because it seems like you're going to get all kinds of great detail on the magnetic field in our galaxy. So this is
there's so much information, and it's hard to parse some of it. So yeah, it's going to be a work in progress for some time to come. But yeah, exciting things.
Absolutely. We had a lot of speculation in the chat as to what exactly the dominant sources of RFI were, especially with regard to day versus night. I don't know if that's been tracked down to a great extent. Probably varies quite a bit.
So this is. I'm just looking to see how many folks from the Chime team are on this call, because they're dealing with this sort of stuff all the time. But yeah, definitely we see more activity during the daytime, just in part, as William mentioned, because of cars, Samantha mentioned cell phone related activity. So yeah, there's a lot of that. I mean, on site, cell phones are not technically not permitted to be turned on, but it's sort of inevitable during
Yeah.
the day that folks coming by, if they have their cell phones on. But yeah, it's just something we have to contend with, and nighttime observations are a little bit better for that reason. But as you saw from Luca's plots, it's not a whole lot better at night. There's still a lot
For
of
sure.
channels that we have to discard. So
So you alluded a little bit to some of the efforts that are going on to remove RFI, to correct for RFI. So how is that going? Because I remember when I was an undergrad and first exposed to radio astronomy, I saw RFI and it sent me running away. I was scared. So, running to the optical.
and it's
So
only gotten worse.
I
So
know.
this is
So
it is sort of a race against time to try and so it's kind of interesting because as the cell phone technology progresses, we get more and more channels with RFI in them. But at the same time, the radio astronomy technology is also progressing, and so our spectrometers are able to sample much more finely and in frequency, and so we can kind of pick out the channels that are salvageable. But there's really nothing to do about it. You just have to discard those channels. It completely swamps the signal, so you can't. There's not really any way to
salvage it.
salvage those. No, not really.
Yes. So Tom chimed in with Tom Landiger with a detailed breakdown. Thank you, Tom.
Yeah.
All the different contributions.
Yeah, Tom can look at a spectrum like that and tell exactly what's what on there. So, yeah.
It begs the question: can a machine do that? In an automated fashion? Is there are machine learning efforts to pick out RFI automatically, or is this not something that's being looked at right now?
I don't know too much about it. I would expect that people are working on that. The techniques we've been trying to use are just sort of, tracking
By eye, yeah.
By eye, but also just tracking. If you look across the spectrum, if there's a wild jump in the value of the power, that's not going to be from an astronomical source. That's RFI. So that's one way to do it. But yeah, maybe I'm not sure if there's anyone on this call who has experience in machine learning with RFI, but yeah, maybe
We
that might be a possibility.
pick Seb's brain about it, I guess, later. Seb Fabro. Yeah. We got time for a couple more questions, one or two, if anyone wants to chime in. Yeah. Terrible. Isaac Cheng, a student, co-op student who's absolutely excellent, by the way. I'm going to embarrass him, who's working with me, points out that Steve Harrison is also using ML to identify transient RFI. So that would be a person to talk to as well.
Great. Yeah.
Thanks, Isaac. Okay, well, I think there are a lot more questions, frankly, but maybe we can agree to email. I know I'll probably email Anna later about some of these since we're at the top of the hour. So let's all thank Anna once again. Virtual applause all around. Oh, William, just under the buzzer if you want to ask one more question.
Well, I wasn't going to ask a question. I meant to applaud, but okay, fine.
Okay.
But since you prodded me, I was wondering about
the kind of worms.
You can work out the large scale structure of the galaxy from these observations. I mean, from the large scale, you can work out, say, the large scale structure of the magnetic field, presumably along the line of sight to some extent. Can you use that to constrain our understanding of the spiral density wave?
Oh, wow. You're asking the tough questions here.
Yeah.
To constrain the spiral density wave, you said?
Yeah.
I imagine so. Again, not exactly my line of expertise, so I don't think I have too much to say about it. But I think one of the difficulties with all of this, as you mentioned, the what we get from these rotation measure maps is just the line of sight component of the magnetic field. And then there's a whole lot more uncertainty in all of these other parameters that fit in as well. We talked about the electron density. There's an orthogonal component of the magnetic field that needs to be taken into account. So yes, I think this can help in constraining those types of models. But there are a lot of
data sets. Yeah, if you use other data sets as well. Then
a lot of pieces that need to come together. That's right.
Okay, now I'm going to do the applaud and not raise my hand. Okay, okay.
Thank you very much.
Thank you.
Yes, thanks very much. Kudos coming into the chat as well. So we'll stop there. You can pause the recording, Sam.